Okay, so we'll start. So any questions? So I think you have done Langevin equations, right, in Sanjib's class, right? Yeah. Okay. So supposing you want to solve this problem. Okay, so now, so I think one way you can solve this is you can just, this is a linear equation. So you can solve and say Vt equals to, right, this is a solution. And then you might be interested in calculating something like maybe V squared T average. Right, so this probably, you know that this eventually at long times, so this will go to, at long times it will, the system equilibrates, so it goes to this value kBt by m, right? So of course, if you use this, this formula, then you can take square and then do some averages, and then you have to take the noise average, and then what you'll find is that, of course, it the system depends on this initial V0, right? This quantity. So at short times, I mean, it will depend on the initial condition, but at long times, this will decay to 0, and you'll get the steady state equilibrium value. Right, but now another way you can solve this problem is by Fourier transforms. Okay, so if you solve by Fourier transforms, you simply take a Fourier transform, and then you get something like omega. This is Fourier transform in time. So many of probably you are familiar with this kind of like way of solving this equation. So this you get V tilde omega is equal to 1 over right, so I can write the velocity in Fourier space in terms of the noise, right? And then of course I can calculate this by just taking V square average and then using the noise properties. Okay, so if you do this, what will you get? I mean, so using this you can calculate V square T again. And so here, of course, you don't see any initial condition dependence, right? This solution doesn't have any information on the initial condition. Okay, so so what you'll, but if you do this average, you'll actually get exactly kBt by m. Okay, so you'll get the steady state answer somehow. So, but you forget the initial condition, and the reason is like you have to ask how did we get this equation? Okay, so if you so to get this equation, what you really have to do is we start with the dv dt, and then do e to the power multiply by time, and then take these limits. Okay, and now to get to this form, you have to do some partial integration, right? And then there's a question of like boundary terms. Okay, so boundary terms, but we want to specify it at time 0, right? Which we can't using this formula, this approach. Okay, so if you want to do it by this kind of a transformation, you really have to do a Laplace transform. Okay, so instead of I omega t, if you to put e to the power minus st and then to 0 to infinity, then you'll get the initial condition v of 0. Okay, and then you can do this problem. Okay, so if you have initial value problem, then if you do Fourier transforms, usually you'll get the like the asymptotic results correctly, but you lose some information. Okay, I don't know if that answers your question. Okay, so for the diffusion equation, it's a similar thing. Like you, when you really do this kind of a thing to the power I omega t and thing, you have to do a like a partial integration, and then you'll see that you don't really get this kind of equation. Okay, so any other questions? Okay, so let me again recap what we did yesterday. Okay, so I had promised that initially that we are going to do some quantum mechanics and also chaos. But so I'm not sure we have time for all this, but we'll maybe try to spend some time at least on doing some basic recap. Okay, but let me again recap of last class. Okay, so we said that usually you can define a marker process in, so there's some configuration space. So there's configurations C, which I specified by C, and then so let's say there are different configurations C1, C2, C3, C4. These are different configurations of a system. It can be the position of a random walk, or it can be the spin configuration of a spin system, or the distribution of particles in some system. And then Markov process basically means I specify transition probabilities between these states. Okay, so from one time to another time step, or in continuous time some transition rates, I have to specify probabilities of transition, right? So these probabilities, I mean, so there are, I mean, there can be transitions in various ways. Okay, so there can be, so each of these arrows depends, describes some transition probability or transition rates. Okay, and then this either in the continuous case, these are this W matrix, elements of this matrix. So this gives the probability of transition, rate of transition from J to I, or in the discrete case, I had probabilities of transition from J to I, right? So this is, I just give transition rates between various states. And then given such here we can write, okay, so if I track the system microscopically in time, then what will I find is that in configuration space, I start from some configuration, and then maybe it remains in that configuration for some time, then it goes to another configuration, and then, so this is some abstract configuration space, right? For a random walk, it's simple. It says the position, so the position, I mean, for some time it just stays in some site, then you go to another site. If so, this is in continuous time. Okay, and then I move to, so again I stay in the same site for some time, and then I might jump to some other state. Okay, so in general, in time, this is what the system is doing, like it's just jumping between configurations. Okay, but then we can also talk of like, so it can be in various configurations, and at a given time, I can ask what is the probability in each configuration, right? So there are all these configurations, and it's just moving between these configurations, but I can ask at a given time, what is the probability that it's in each configuration, okay? So, so then we define this probability of thing in a configuration C at time t. And then we said that this, the equation is basically given by okay, and so this is the W matrix. Okay, so one thing should be clear. Then we said that the system at long times it reaches a steady state. Okay, so this W matrix has some properties. So one of which is that C prime sum over C is equal to 0, and then this ensures that there's a left eigenvector. So left eigenvector basically means I have this matrix, and I can write a row vector on the left, 1, 1, 1, 1, such that the action, sorry, summation is over C, right? Yeah. No, this is C prime, sorry, this is C prime. Because this is probability of transition from, so it's what's the probability it's in some state C prime, then what's the probability of transition from C prime to C, right? But yeah, so but here the summation is over C. So it's the, okay. Okay, and so then this basically says I have some matrix and I have a row vector here. And then the basic idea is, okay, so let's say I have some matrix like W11, W12, W13, let's say for a 3-state system. So in this case, if I, so this is my, I take a state which is 111. And here I can see that what do I get? So I get basically the first, okay, so what do I get? First element. So I'll get a row or a column. Huh? Out here I'll get a row vector or a column vector? Row vector, right? So the first element is W11 plus W21 plus W31. Right, and the second element is W12 plus W22 plus W32, and the third element is W13 plus W23 plus W33. And so what are these? 0, right? Because of the property that the columns are 0. So this is 0, 0, 0. Okay, so this is true for any Markov matrix. Because the columns are 0, there's always an eigenvector like that. Okay. And then, so there's a 0 so there's some left eigenvector with a 0 eigenvalue, which means that there must be some right eigenvector with also 0 eigenvalue. Okay, so this means that, so this one, what we called it some chi0. And this left eigenvector is denoted by the symbol chi and with this. And the right eigenvector there has to exist a right eigenvector with the same eigenvalue, 0. And this, of course, won't be 1, 1, 1, right? Because that is no longer true. In general, it can be quite complicated and it's difficult to find. But there exists such a state, and this corresponds to the steady state. Okay, so okay, so I don't know, maybe I should, like, I think some people asked, like, between this, is it clear that left eigenvalues and right eigenvalues should be the same set of eigenvalues? So how do we prove that? Right, yeah. So what you can see is that, okay, so what does it mean to find a left eigen? So we are basically saying some state chi is equal to, let's say in general, some lambda chi, right? So this is equivalent. So this is just like a matrix. This is a left vector. Okay, so if I take transpose of this, then I get W transpose chi is equal to lambda chi, right? So which means basically the skies are the eigenvalues of W transpose. So if I have a matrix and a transpose, they have the same set of eigenvalues, right? Because to find the eigenvalues, you would have to do something like W minus lambda I determinant equal to 0. And if you take transpose, obviously you'll get the same set of eigenvalues. Right? Okay, another way of looking at it is, okay, so supposing I know the right eigenvalues, okay. So then we know that we can construct a matrix U from this right eigenvectors such that this is true. So this is the matrix of eigenvalues. Right? This is clear for everyone, right? So now if I multiply by U inverse on both sides, I get this. So this is what usually we say that we can diagonalize a matrix with some transformation like that. And now I can also write it like U inverse W is equal to lambda U inverse. Okay. So this really corresponds to, so if I construct U inverse, that really gives me the left eigenvectors, right? Because U inverse, I mean, it consists of like, so these rows are the left eigenvectors, basically. Okay. And you can see, obviously, the eigenvalues, it's the same set of eigenvalues. Okay. Okay, so, yeah, so this is, what we said about here. So, and then we said the okay, so one thing should be clear that when we say it goes to a steady state, doesn't mean that the system is stuck in some configuration, right? So in configuration space, it's still moving, it's just going around things. But if I do a large number of experiments, I'll find that there's a distribution which doesn't change with time. Yeah. No, it's the same. I mean, see, both I'm right doing the same thing more or less. Yeah, I'm assuming everything is diagonalizable and like, yeah. In the, yeah, maybe, okay. But of course, I should be able to find, I should be able to find eigenfunctions and all. In that sense, it's diagonalizable. Yeah, there might be some subtle things. I'm just in the most simple case, these are like true. Okay, so let me again explain this point about steady state. So if you have, let's say, particle in a box, like in a 1D box, and then so let's say this is the box. Okay, so let's say this is the box from 0 to L. And I start a random walk from some point. Okay, and this is time. Okay, so then of course, if I look at one trajectory, it will it does something like that. Right. If I look at another trajectory, it will do like that. So every time I start from the same initial condition, and I'm looking at different trajectories. Right. So so basically now now if I can either take lots of trajectories, or the equivalently what I can do, I can start a large number of particles from here and see what they do, right? Because then, let's say non-interacting particles, then it's the same kind of thing. Then basically the statement is that initially, of course, if you start from a large number of particles, then you'll find that the distribution is basically distribution looks like, so this is 0 and L. Distribution looks like that. And then the distribution is slowly changing, and it's going to a, so with time the distribution spreads, and then eventually it goes to a, so at long times it goes to a flat distribution, okay. So if you start with large number of particles, finally everyone is uniformly distributed. But if you look at individual guys, they are of course moving around, right? So steady state just means that on an average, things are not changing with time, but each guy is still doing is still evolving. Okay, any questions? Okay, so for the random walk, we computed things like expectation values of operators, of observables, like what is the mean position and x square and so on. And in general, for any Markov process, so you can, so any observable is a function of configuration, right? So is a function of, expectation of observables. Okay, so any observable is basically a function of some configuration. Okay, so for the random walk, it was like x is obviously a function of A, and if you have a spin system, our observable could be something like let's say sigma 1 times sigma 2. That's an observable. It's something with some function of the configurations. Okay, of the variables specifying the configuration. Okay, so some function, and now if we can ask what is in general at time t, if I make a measurement, what is the expected value? right? So what will this be? So this is basically given by sum over all configurations, A, C, and then probability it's in this configuration C. So this is obviously the definition. What's the probability at time t? It's in some configuration times the value in that configuration and sum over on. So this is the expectation value. Then the other kind of interesting question in this kind of stochastic processes is like correlation functions. So you might be, if you have two observables, you might be interested in finding A t, B t prime. Okay, so basically you make a measurement at time t and you make a measurement of this observable in time t prime, and then you want to ask are they correlated or not. So if you want to measure this, okay. So given that this dynamics is specified by this W matrix and all, how would you calculate some quantity like this? Okay. So here because this is 2 times, what you need is the joint probability that the system is in configuration. Some configuration at time t and in some other configuration at time t prime. So this is basically should be given by something like this, sum over C, C prime, and then A, C, B, C prime, and then I should say probability it's in configuration C at time t and C prime at time t prime. Okay, so this is the okay, and let us assume that t is greater than t prime. Okay, so now how do we calculate this? Okay, so this of course we can write it as equal to the. So this is the given it's at in t prime at time. Given that it's in c prime at time t prime, what's the probability that it will be at c at time t times what is the probability that it was at C prime at time t prime? Okay, so I mean this is obviously true, and how do we compute this object? Okay, so this how would you compute this? From what we know, would we be able to compute this from the, let's say, the rate equation? This is easy, right? Because see, when we solve this equation, del Tp, so this is our basic equation, and here what do we say? That the initial condition is at C prime, at some time t prime, and we want to know that it's in some other state at C at time t. So of course we can then solve this equation with this initial condition at time t prime. Instead of time 0, we just say that at time t prime it was in this configuration, and then the usual solution. So the usual solution is of course Wt, Pt is equal to e to the power Wt E0. This is the solution, but now P0 we want it to be C prime. Sorry, not T. So this should be now what? T minus T prime into P of T prime. So we want to evolve from time T prime to T. So then obviously we'll get T minus T prime here. And this PT prime, we want it to be C prime. Right? So therefore, okay, and then given this, if we want what is the, so this will get some probability vector, and of course then out of that one of them will be this configuration C, and so we just need to pick out that element, right? So this object E of Ct given C prime, T prime is equal to basically C prime AC into 2. Okay. So therefore, I mean, at least it's clear that given this equation, we should be able to, if, like, just compute things like this, correlation functions and all. Okay. So that's what's important for Markov processes. Like, just this equation and the initial distribution is enough for you. Like, you can compute all correlation functions, all expectation values, and so on. And yeah, so this is the basic. Yeah. Okay, so I mean, so I'll just give this as an assignment. I mean, if you have, maybe you can do it in the one of the tutorials. Like for the spin dynamics, you can calculate things like. So one thing is you can calculate what is the expectation value of the average magnetization, right? And then you can try to compute something like sigma 0, sigma t. For that, for whatever dynamics, this Monte Carlo dynamics that we wrote. So, yeah, I mean, using whatever we had got. Okay. Okay, any questions on this? So, yeah, so if there are no questions, I think we will maybe move to discussing a bit about quantum mechanics. Okay, so. Okay, so what I thought I'll do is also try to, because it looks very similar, right? This frame formalism and formalism like that you use in quantum mechanics. So also try to see the differences from this kind of Markov process and quantum process, which mathematically look a bit similar, but it's kind of interesting to look at the differences. So, okay, so. So this is some. Okay, so again, we'll talk about systems with example. So this is a, so the dimension of the Hilbert space is L-dimensional. and then the other example is so if you have n spins, so what is the dimension of the Hilbert space? 2 to the power n, right? So yeah, 2 to the power n. And you can, basic states are basically this. Okay, so this is. Okay. Okay. And then let's say, so let's talk about, so this is example 2. So for example 1, I mean, basically the general state. So, so basically, there's any arbitrary state, I can represent in terms of this basis vectors. Okay. And again, basically, what this, I mean, this is just a L-dimensional vector, right? So, I mean, the state psi is basically a vector with elements psi 1. Okay, I don't, right now I'm not looking at time dependence, so let's just call psi. So, psi 1, psi 2. Okay. So a state in quantum mechanics is represented by a vector like that. Okay. So this, of course, looks. Okay. So this looks kind of. Where we said that a state can be represented as equals to sum over. So now, okay, so this is x equal to 1 to n. Okay, now, so the differences are, of course, so this is in quantum mechanics and this is Markov process. So both have kind of a similar representation. So one is psi of x can be complex. And here P of x, so these are amplitudes, right? So psi of x are complex amplitudes in general. And P of x is, of course, has to be real, and they are greater than or equal to 0. Right, and then here, I mean, so P of x here represents probability of x, and here so obviously these things are also all less than, have to be less than 1, P of x, and here xi mod square also has to be less than 1. So this is all, x is discrete and it's a finite space. In the continuum, again, of course, things are different, but these are the differences. Okay, now let's write the time evolution. So then we are interested in how does this state evolve in time. So so again, so this is quantum mechanics and this is Markov process, or let's call it random walk. Okay, but okay, in general, it's any Markov process. So here the equation is, of course, I del t psi. Right, and so now what are the properties? So this is, I'm putting H cross 1, and so this is the Hamiltonian, right? Usually it's Hamiltonian of the system. And what are the properties of H? What's the most important? It's a Hermitian operator, right? So H is, so usually it's the Hamiltonian. And so that's Hermitian. So which means that H dagger is equal to H. So if I take transpose and conjugate of this matrix, it's the same. Okay, and here, of course, the equation looked very similar. So I had equation for the probability distribution, which looks like this. And so this was the W matrix. And the really important properties are so one is that all elements Wij are greater than equal to 0 for I not equal to j. Right, all because these are transition rates, they have to be positive numbers. And then 2 is that you have this rule. Right, so this is an important, this is conservation of probability. So here actually the being Hermitian ensures that this probability, total probability will be conserved. And here this property ensures that the total probability will be conserved. Okay. And then using this, you can do things like, these are what is required for this, proving things using Perron, Frobenius, and so on. And you can prove many things like existence of steady state and convergence to steady state and so on. Okay, so these are the important properties of a Markov matrix. Okay, and then the solution is, we can write the solution of okay, so here, of course, we can write a solution as psi t is equal to e to the power minus I 0. And then the important thing is that this is a unitary operator. Okay, so this is U T. Which means that basically ut dagger into ut is equal to identity. Okay, which of course follows from the fact that H is Hermitian, right? So this is yeah, and this of course ensures that if you take okay, so yeah, so if you take, so this is the norm of the state at time t. And then because of this unitary property, this is always 1. Right? So this you can just see easily. And for the corresponding probability vector, we have P at time t is equal to e to the power Wt into E of 0. This of course doesn't have the unitary property. But you can again prove norm by basically using this result. So here norm means what? So here norm means sum of the, so here norm means sum of xi mod square. So that's why this is the norm, right? But for the probability case, it's just the sum of the vectors. So the norm is really, you can write as what we discussed actually. Huh? Right, yeah. So there's this left guy which is 1, 1, 1, 1, 1 times P of t. This is the norm because this really gives me some of the probabilities. Okay, and this object will be what? So using this, this is equal to chi0, 0, and then we need that this should always stay 1, right? So that you can see by basically looking at this object, and you see that this is chi0, and then you have 1 plus, supposing you just expand this, wt plus w square 1, 0. Okay, so now, so the first term is chi0, p0, and then the next term is chi0, okay, so now what is this? This is 0, right? Because W acting on chi0 is, we said it's 0. And similarly, W square and everything will be 0, right? So all these states are 0. So all these things are 0. So you get basically chi0, p0, and this is the initial norm, right? And initially, we always want to start with a normalized state. So therefore, this is equal to 1. Okay. So again, we see that the probability is always conserved. And basically, what is important is we use this property of the matrix. No, see, because you are starting with a it has to be. It doesn't make sense to start with a probability distribution which is not normalized. Yeah. No. Any vector, like I'm saying, you start with any initial condition. Let's say you have 4 states. Okay, you start with any initial condition, but of course you need that sum should be 1 always, right? Because you, okay, and then you're taking product with 1, 1, 1, 1. But this is basically equal to P1 plus P2 plus P3 plus P4, right? So it is 1. That's, I mean, just initial state is normalized, which is. What is the meaning of? Of? JJ. It's just the total probability going out of the state. I mean, the transition rate out of the state. I mean, like you have a, like if you have a spin, so it's going, I mean, it's going to this state. So that's basically the JJ component, right? See, when you wrote what is the probability dp up, let's say dp up by dt. Right, so there's some rate at which things are going in, which is, let's say, a positive rate lambda p. So let's call this lambda 1 p, p down. So that's things flowing into this. And then there's something, because there are transitions from out also, right? So that's a negative rate, p up. And then when you, no. That is if you, this is a very, you have to maybe just write things. So when you do the discrete thing, then it has that interpretation. See, because staying probability would always be positive, right? But the diagonal elements are, see, it's all negative. Diagonal elements are by construction all negative, right? That's what we have been writing. Diagonal elements in this in the continuous time representation, diagonal elements are always negative. In the discrete representation, it's all positive. Okay, so maybe let me just explain with the example. Okay, so let's say we have this two-level problem, okay, and we say we write a discrete yeah. So what is the probability that I am in upstate at time n plus 1? Okay, so then this is what? What is the probability that I go from down to up? Okay, so there's some transition probability. Okay, so let's call that probability P. Okay, so this is probability of going from up to down, down to up, and there's a probability of going this way. That's I call Q. Okay, so these are probabilities, not rates. Okay, so this is P times probability it was down in the previous time step, right? And then there's a probability that I'm in up, but I don't go here. There's staying probability, right? So then I write plus, what? 1 minus? 1, no. It says 1 minus Q, right? And there's a probability of going to is Q. The probability of staying is just 1 minus Q. So 1 minus Q, and then probability that I was already up at time n. Okay. And then what is P down n plus 1? So what is this? So I'll get some contribution from that it was already down and it stays down. So what is that? 1 minus P times P down n, and then Q, right? This is okay, right? Okay, so now let's write the matrix. So the matrix is P 1 minus Q minus P and Q. Okay, so this is so is this a W matrix? No, this is what I called a T matrix, right? This discrete time, so I called it a T matrix, and the property was that the sum was 1, right, not 0. And now here, of course, you see everything is positive, like all diagonal elements are. So in discrete time, this T matrix, everything is positive, and the property is that the sums are 1, right, instead of 0. Now, supposing I'm trying to go to this continuum limit, okay, so then what am I doing? So when I go to the continuum limit, basically it corresponds to taking this minus the state at time n, right? So basically what I'm doing is I am taking this vector P up n plus 1, P down n plus 1 equals to okay, and then I'm subtracting P up at n, P down at n. Okay, so because this will give me like, then when I make, so n is like time, and then I'm going to divide by tau, and that will be like del P del T, right? So if I subtract this, so subtracting this is like subtracting a unit matrix from this guy. Is that? Which one? Here. Then okay, maybe I made a mistake. Okay, up. Oh, it should be, maybe I should, no, this I should, here I should write the same thing, right? In the same order. So here I should write, what is the probability it was up. So this should be 1 minus Q, and this should be P. That's better actually. Q and then 1 minus P. Okay, this is better actually, yeah. Otherwise it's, this is the matrix. Okay, so yeah, so that's good. Okay, who found that? You found it, is it? Okay. Maybe several people found it, okay. So now you want to subtract this. So subtracting this means basically subtracting a unit matrix from this, right? Because, okay, so if I subtract a unit matrix, then I see that this becomes 1 goes. Right? So when I do this, I get minus Q, P, Q, and minus P. Okay, and here, of course, it's the same. N. Okay, and then I basically divide this thing by time tau, right? When I divide by time tau, and then the left-hand side becomes del T of T up T, T down T is equal to okay. And then we see this, now of course this is what we called the rates. So these have dimensions of rates now, right? These were dimensionless objects. These are just probabilities. Now these are rates, and they can be, they are 0 to infinity, right? Rates can be anything because, then I have to take some limits. I have to take the limit q going to 0, tau going to 0, such that q by tau is some finite number. Let's call it lambda 1. And similarly, p goes to 0 with p by tau finite, and I call that lambda 2. Right, so then I basically get minus lambda 1, lambda 2, lambda 1, minus lambda 2. Okay, so now this is what I would call a W matrix. Right, and this, of course, has a different property, right? The diagonals are all negative, and because now this is basically telling me the rate of things flowing out. Earlier it was probabilities, right? And now it's the rate at which things are changing. So the diagonals are just rate at which things are, the probability is flowing out. So that's why these are negative and these are all positive. Okay. So anyway, just make sure this, when I was a student, it took me a long time to, I was also confused about this, but you just do some simple examples and it will become clear. Okay, so, okay, let's get back to this. Yeah, any other questions? This point was completely clear, I hope, right? Okay, then where were we then? No, where did I write 1, 1, 1? The chi. See, chi0 is not a probability vector. See, the left, these eigenvectors need not be probability vectors. It's just an eigenvector of this matrix W, but it's not a probability vector. Okay, so 1, 1, 1 can't be a probability vector. Why? Sum is not 1, right? So it's not a probability vector. The right guy is an eigen, of course, phi 0 is the only eigenvector which is also a probability vector, but all the other eigenvectors are not probability vector, like valid probability distributions. Okay, any other questions here? Okay, so yeah, so we were discussing this. Okay, so okay, so in general, like in quantum systems, sometimes the evolution can just be given by a unitary operator, and you need not even specify the Hamiltonian. Okay, so you can just say that in time t, it evolves as with some unitary operator. Okay, so psi t equals to u psi 0. Okay, where u has to be unitary. That's I mean, so sometimes you don't need to specify the Hamiltonian where it came from. Okay, so this is a good description already. See, chi naught is always 1, 1, 1, 1. But steady state can be very, like, I mean, so yeah. How will you find? No, you can't. I mean, yeah. Yeah. That will still give 0, right? Yeah. See, but the, no, see, it's, you're asking whether it's a steady state or not. No, it's not, because the steady state is a right vector, right? So this is the equation. So what I want for the steady state is that it should be some state, some vector, which is a column, which should give me 0, right? So if I find something where the left guy is 0, that doesn't help. That's not, because this is what is required, right? It has to be a right eigenvector, because this equation is in terms of right eigenvector. Yeah, that's normalized. That's I used it somewhere, right? I used it here. Yeah, chi0 phi0 is of course 1, and right, yeah. 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 No. This is n. This is just one condition, right? And this has n like if it's n vector n components, so you can't find it. That's from one. Okay. But yeah, in general, see the basically when you write, uh, so we said that this chi's and phi's, so they satisfy two properties. Okay, so chi n phi n equals to delta nm, and okay, so this you can they satisfy orthogonality and completeness. Okay, and this actually it's equivalent to saying that when you construct this right eigenvector u, of course u inverse is equal to 1, and also u inverse is equal to identity. Right? So I mean it's just that statement. Okay, now what was, oh yeah, so we are talking about, okay, so we are keeping going back to probability, but anyway, so okay, so this is one statement that, so we have in quantum mechanics, states are described by wave functions, and these are vectors which have complex amplitudes, and the time evolution is given by some unitary transformation. Okay, and then the other important what result in quantum mechanics or theory of quantum mechanics is about measurements. Okay, so the measurement postulate. Okay, so here in the Markov case, we talked about measuring observables. So observables were basically some functions of the configuration space, and then we know how to calculate expectation value and so on. So in a quantum mechanics, okay, so first of all, I mean observables are given by some, in general, any are given, described by, are represented by, again, Hermitian operators, right? So Hamiltonian is, of course, one example, and the eigenvalues correspond to the energy of the system. That's observable. So Hermitian operators. So let's say, so let's say A be some observable. So Hermitian means A is equal to a dagger. And then, so this, so it's a Hermitian operator, so I can find real eigenvalues. So let I or I. So which means basically that A acting on this vector AI gives me a real number times AI. So and so Hermitian means okay. So Okay, so basically, given any observable, there is a corresponding Hermitian operator, and then it has eigenvalues and yeah, and typically they will form a complete set. So now, when you make a measurement, okay, so then what the measurement postulate says is that so we'll basically get the value. Uh, So when we make a measurement, we'll of course find one of the eigenvalues, and then it says that there is a probability that you'll find an eigenvalue AI. So probability of finding AI is equal to, let's call it PI, and that is equal to what? AI psi, right? AI psi. So given that the system, okay, so, given system is in arbitrary state, and then mod square, right? Mod square. So this is the probability of measuring in state psi. Okay, and then the other thing that also follows from the postulate is that immediately after the so if I measure an eigenvalue AI, then immediately after the measurement, it's in this state. Okay, so this is also one. So it basically that's the collapse of the wave function. So every time I make a measurement, it collapses to some eigenstate. Okay, so this is the most simple statement of the measurement postulate. You can like in general, you'll need more complicated statements. Okay, so then you can ask for what is the expectation value. I mean, so expected. Okay, so clearly, I mean, A expected. So when I make a measurement, I can get different values, and the expected value is of course sum over AI. So what's the probability I get to measure the ith AI value, and what is the times AI, right? So this is of course given by AI, and then PI is given by this object. So that's psi. So that's the amplitude square, and then we can write this as so I can write this as sum over. because A acting on AI gives AI, right? So I can put this operator here. And now, because again because of completeness, this sum is 1. So basically this I get as psi. So that's the expected value of the measurement. Okay, any questions? No. Okay, so we'll just do one example of okay, so let's look at again this kind of, so this is like an example which is almost like the 1D, like the random walk, okay. So we'll consider, so there's a lattice, and you have a particle. So this we described that you can have a particle on a lattice, and basically the state is given by psi is equal to sum over x. Okay, so this is really the position representation, right, of the waveform state. So this is the basis. I'm expanding it in some basis. And so we'll write a dynamics, which basically is like like the random walk, but it's the dynamics of like, so I think many of you would have seen something called the tight binding model, which is a model of electrons like free electrons on a lattice. Okay. So then the dynamics of this wave function basically looks like I some lambda Okay, so this again you can see that this is kind of like the, so if you take the continuum limit, this would just be del 2 psi by del x square, right? So that's like a free particle evolution, but we are doing it on a lattice, so that this is the lattice version of this model. Okay, so okay, so again here you can ask the same question, like you can ask if I start a particle in some initial state, how does it spread in time? Okay, and then what? How does the width grow and so on, right, for this yeah. So okay, so then how do we have to again solve this equation? So it's the same kind of mathematically, it's exactly the same equation. So how do we solve this equation on the infinite line? How you get this? Why? No, so I'm just writing like a model of an electron on a lattice. So some dynamics, so this corresponds to some Hermitian. Where do we get this? Okay, so corresponds to, if you know about the tight binding Hamiltonian. Okay, so but okay, so if you don't know the tight binding Hamiltonian, the simpler way to think about it is, okay, so at least this equation I guess you know. In the continuum, let's say you have okay, right, this you know, okay, and then I discretize it. It's like the second derivative, right? So that's okay. Okay, so one is like it naturally comes if when you talk of the tight binding Hamiltonian. Okay, so that's like basically you have a crystal, and then there's some potential that the electron sees, and then you try to. So after some approximations, you can write an effective Hamiltonian, which basically corresponds to like this kind of yeah. Okay, so Yeah, so for those of you who have seen a tight binding Hamiltonian, so it corresponds to some uh, if you write a Hamiltonian like this. Okay, so this is so for those who have seen this, I mean, if you write some like Hamiltonian in some second quantized notation, where there's a kind of a hopping term and then there's some on-site potential. Okay, so this is like an on-site potential. This is the number of particles at a site, and this is hopping terms. Okay, so in general, this could be different in like usual tight binding models, but I just set it to just to get the kind of discrete Laplacian. Okay. So for this kind of model, of course, you can put n electrons, but if you put one electron and then ask how the wave function evolves, then you basically get this equation. Okay. Yeah. This ratio. This one, yeah, no. So here it need not have been. I mean, in general, I could this any number is fine. In general, I can put EL. So that is also a valid model. Then I would get like I would get instead of 2 here, I would get EL. Okay, so that's also valid. That's a more general thing. I'm just looking at a special case where I set this to 2. Is that okay? Okay, so okay, so I mean, yeah, so here, of course, like in this quantum case, these amplitudes, I mean, the factors that you would put here are like less constant than the random walk, right? In the random walk, there's some constraints on what you would put here because there's this condition of the columns have to sum to 1 and so that. Here, you have more freedom, like they can even be complex and so on. So otherwise, but this is a special case where they have the same structure. Okay, any questions on this? Okay, so now how do we solve this equation? We solved it for the random walk, right? We wrote a very similar equation and got the solution at time t. So here, what was the method? Fourier series, right? So again, it's a lattice, so we just take Fourier series. So basically multiply this equation by e to the power I x theta and then sum over x. Okay, so if you do that, then you get psi tilde t is equal to and so you'll get equation I tilde t. Okay, so this is what you'll get. I mean, when you do this thing, and then of course solution is again similar. So psi tilde theta t. Okay, and then we consider a situation where you start from the origin. So then what is this is 1 again. Okay, so we have to, because this is like a delta x0, so this is still 1. So it's just this, and then we took the inverse transform. So psi of xt is equal to 1 by 2 pi. Okay, so this is the solution, and then so in the classical case, it's only there's I here, otherwise it's exactly the same, and there's a minus sign in the classical case for the random walk. And so this thing is basically, it will give you, so I think in this case you get a Bessel function. So this is equivalent to some Bessel function. And if you change I to, if you remove the I, you get a modified Bessel function, okay. So, so that's the only difference. Now here, what you can show is that, so in the classical case, if you started with a particle like that, then what we saw is that it almost spreads like a Gaussian, right? So it will be some Bessel function, but at large times it will look like a Gaussian. So if you plot it, I mean, it spreads like that. And in this case, then the important thing was that this width goes as square root of t. Right. So now in this quantum case, again, you can ask the same thing. Like you start from weight 1, and now this evolution is completely different. Okay. So here, because it's because of this factor I, what you'll find is that it actually spreads like so. It has some. So basically, you have to plot the Bessel function, and you'll get something like that. Okay. So, so there's no central peak. There are two peaks at the edges, and then this thing spreads as t. So there's a front which basically goes as t. Okay. So this is ballistic spreading. So sorry. So this xt square. So this is the classical random walk where you plotted probability. Here again you ask the same question, psi mod square, but because of this complex things you get like interference, and also you get all these oscillations and this ballistic behavior. No. This is infinite line, on the infinite line. So yeah, so there will be some front, right, and then after that it's extremely small. Yeah, but if you put a wall, of course, you can ask what happens. Then, okay, so then, of course, will it reach a steady state, for example? Okay, so if you put a, yeah, so in, yeah, so if you take a finite lattice, then for some time you will see this kind of a spread, and then it will eventually hit the wall. But in this case, you don't have any any results like the stochastic case, right? Stochastic case, it will always go to a unique steady state. But here there's no, because, okay, so the solution here is basically psi of t is equal to sum over, so we wrote it as e to the power minus I h t into psi 0. Okay, and then this, of course, if you put this some complete set of eigenstates, you can write this as sum over, so let's say n. So supposing you find the eigenstates of the Hamiltonian, and so they form a complete set, so you can insert it in this thing. And then, of course, because H acting on phi n is En, you get some e to the power minus I E n t phi n, and this is like An. Right, this is the initial amplitude. Okay, so this we wrote even for the master equation. So there was some amplitude, and then this is for each state. Okay, and this ANs are found from the initial condition. Okay, so now in the Markov process, what happened was there was one zero eigenvalue, and all the others decay to 0, right? So we converge to a unique state. But in this case, all these are always real. ENs are all real. So basically, it's always a sum of this large number of phase factors, and so you don't get a unique steady state. Okay. So basically it will keep evolving and doing things. Now you can ask whether it has statistical statistical properties and properties or not. So that's actually, I mean, if you take like many quantum systems, that's one question is like, it seems that even with this kind of a dynamics, you can get thermalization and so on. Okay, so that's some very interesting area. Yeah, right. Yeah. So right now we are just using the fact that they have a similar structure, mathematical structure, and we are trying to point out the differences. I mean, this is of course a quantum particle which is moving. Right. Yeah. This is not a. Yeah, it's not a. I mean, okay. So how would you define a quantum random walk? Yeah, so there are, I mean, like, there are some models of quantum random walks which are very similar to this. So there's, okay, maybe, yeah, so I had said I'll talk about quantum random walks, but need not be ballistic. So for example, if you have, like, let's say, if you have disordered potential, okay, and then you do this problem. So you start from electron in some state. Okay, so in one dimensions, what you know is that there's something called Anderson localization, and this someone was talking about it. And then things don't evolve at all. Okay, so if you start from a state, it more or less stays like that. Okay, if the particle is evolving in a random potential. Okay, so random potential basically means when I write this equation, I put a random term here, right? Okay, so if I just put something, let's say epsilon xt, which is a random function of position, okay, and there's no time. It's just a random function of position. In that case, if you can still diagonalize this matrix and look at the eigenstates and then see how it evolves, you'll find that it doesn't evolve, okay? But if you do this in, let's say, 3 dimensions, like again, you consider a 3-dimensional lattice and where each site has some random potential, then if you start a particle, you'll find that it actually diffuses. Okay, so it yeah, so it will basically then if you look at xi mod square, so this is in 3 dimensions. Then it will basically evolve like a Gaussian distribution. Okay. Right. Yeah. So so mixed state means, okay, so you're talking of like some state which is described by density matrix, right? So density matrix, of course, if it's a pure Hamiltonian system, then the density matrix basically evolves like, I mean, U rho, U dagger, okay? And in this case, of course, again, you won't get a convergence to a unique state. So, but if you, of course, look at a subsystem, right? So let's say you have a quantum system, and you break it up into a subsystem and what you call, let's say, the environment. Okay, and this environment is really huge. Okay, then when you look at the kind of the reduced density matrix of this subsystem, then this guy effectively acts like a let's say a heat reservoir, and it has both noise and dissipation. Okay, and then of course you can show that this can go, it will go to a unique steady state. For example, it will, if it's a thermal reservoir, of course you know that under some conditions this will go to a basically the like the Gibbs distribution, right? So the Gibbs distribution is a mixed state where everything is like in energy representation is diagonal. So it goes to the right. Yeah, I mean. No, it's not necessarily the entanglement. I mean, like, you know, I mean, this is okay. This is a complicated thing. I think maybe we don't discuss. Yes. if you have a iterative, iterative means, what was iterative? In which term you have iterative? No, I mean, see, Hamiltonian, okay, so first of all, it has to be, so you have to define what is, because it's a operator, right? So you have to define a random, yeah, you can put a random field. Right, yeah, you can do that. And then you want to ask what? Oh, you can you get unique steady states? No, that, I mean, if as long as its evolution is like that, you don't have a result like that, right? Because there's no, I mean, because it's still, this is still true. Even if you have whatever random field, as long as it's Hermitian operators, even it's whatever random function, this is still true. Okay, but I'm saying like I discussed in this case, effectively you might get diffusion, and then of course it will look like you reached a steady state in some sense. Yeah. Okay, so maybe I'll just stop here. So basically, I mean, I tried to give you some idea of, I mean, I never defined what a Markov process is, but I just gave an example of a Markov process, random walks, and then spin systems, and I talked about these properties of like the W matrix, and we worked out some simple examples. So, okay, so what I'll say is that you should basically try to make sure that, okay, so one thing is like work out the simple examples, make sure that you understand the simple examples well, and other thing is maybe the simple examples like a single spin in a magnetic field. It's good if you can, if you actually do a simulation and look at various things. Okay, so you can, for example, look at the trajectory of the spin. Okay, so it stays up for some time, then goes down and does something, some dynamics. And just try to calculate various things like correlation functions, calculate it from the simulation and from the, and compare it with what you get from the theory. So if even for a single particle system or for the random walk, if you calculate, do this exercise, then that's really useful. Okay. Yeah, so any questions? Okay, so then, yeah, so we break for tea, I guess.